Hello everyone. In this video, I am going to discussing about the how to solve the compound bars problem with one example problem. So let's see the problem. Figure shows the three magnesium alloy bars, each of area 2500 mm square. A compressive load W is transmitted to the bars through a rigid plate. The outer bars are 1000 mm long, while the middle bar is little shorter, leaving a gap of 1 mm. So first one is find the load required to just to close the gap. Second one is find the downward displacement of the rigid plate when a 300 kilonewtons load is applied. Take Young's modulus of the magnesium alloys is 4.5 into 10 to the power 4 Newton per mm square. So let's see the solution. And first we have to solve the question A, that is the find the load required to just to close the gap. So the gap is 1 mm. So question is asking that how much load is applied to close this gap. So first we have to observe the diagram and understand the problem. Here gap between the outer bars and the inner bar is 1 mm. So when we applied the load up to the 1 mm, deformation is possible only for the outer bars. Because of in this condition, load will be carrying only for outer bars. So the gap is 1 mm. So which means, so when you applied the load, deformation is possible for the outer bars. That deformation value is 1 mm. So we know the deformation and we have to find the how much load is required for the deformation. And we know the relationship between the deformation and the load. That is, let us consider the deformation delta and the load is, let us consider the W. So delta equal to WL by AE. So first we have to write down the given data. Here just to observe the problem. 3 magnesium alloy bars, each of 2500 mm square area. So in this problem, deformation is possible for the only outer bars. So 2 outer bars are there. So each bar area of the each bar is 2500. So here having the 2 outer bars. So cross section area of the outer bars is 2 into 2500. That is the 5000 mm square. And we know the deformation relationship between the deformation and the apply load, that is the delta equal to WL by AE. So here delta is nothing but deformation, that is nothing but gap between the outer bars and the inner bar. So that is the, let us consider delta equal to 1 mm, and W, that is we have to find how much load is applied to just to close this gap. And L equal to length of the outer bar, that is given that one 1000, and A is cross sectional area of the outer bar, that is the 5000 mm square, and E is nothing but Young's modulus of the magnesium. So here only one material is there, that is the 3 bars are made by the single material, that is the magnesium alloy. So E value is the 4.5 to 10 to the power 4. So substitute all these values in this equation. So we will get the W equal to 225 kilonewtons. So next we have to find the downward displacement of the rigid plate when a 300 kilonewtons load is applied. So let us consider decrease in length of the outer bar, that is delta, is nothing but deformation of the outer bar is delta. So then what is the decrease in length of the middle bar? Obviously it will be delta minus 1. So here let us consider if it is the deformation of the outer bar is happened 10 mm, obviously here it will be happen 9 mm. Why mean? Here gap is there 1 mm. So if it is the deformation in the outer bar is the delta mean, then deformation in the middle bar it should be the delta minus 1. So next one is we have to find the strain in the outer bar, that is the epsilon naught. We know that when the strain is nothing but change in length divided by the original length. Here we are considering the change in length is the delta and the original length is the for the outer bar, that is the 1000 mm. Similarly, you have to find the strain in the inner bar. So here inner bar or maybe middle bar. So strain in the inner bar, that is the epsilon I. So that is the change in length of the inner bar divided by the original length of the inner bar. So in the problem you have to observe that one. So that change in length in the inner bar is delta minus 1 and the original length of the inner bar is 1000 minus 1, that is the 999. So next you have to find the stresses in the outer bar. So let us consider stresses in the outer bar, that is the sigma naught. We know that one the relationship between the stress and strain. So stress equal to strain into the Young's modulus. Same thing here also I am writing. So delta naught, which is the stress in the outer bar, equal to epsilon naught, that is the strain in the outer bar, into the E naught or maybe the E. So I mean 3. So both of the all the magnesium bar is made by the same materials. So it will let us consider E only. So here stress in the outer bar, that is the sigma naught, equal to the strain into the Young's modulus, that is the E. So we know that one the strain in the outer bar, that is the delta by 1000, so into the E. Similarly, you have to find the stresses in the inner bar, that is let us consider sigma I equal to the strain in the inner bar into the Young's modulus. So we know that one the strain in the inner bar, that is the delta minus 1 divided by 999, so into the EI. So next one, see after the deformation of 1 mm for the outer bar, so load will be distributed to the all the 3 bars is nothing but applying load W equal to the load carried by the outer bars plus load carried by the inner bars. So we know that one load can be we can be expressed in the terms of the stresses, which is equal to load equal to the stress into cross sectional area. So here load on the outer bar we can be write down the, that is the sigma naught into the cross sectional area of the bar, that is the A naught, plus load on the inner bar, which is equal to the sigma I plus AI, equal to the applying load, that is the given in the data, that is 300 kilonewton. So 300 into 10 cube. So next we know the sigma naught value, that is the strain into Young's modulus. So here you have to substitute sigma naught A naught plus sigma I plus AI equal to 300 into 10 cube. In the place of sigma naught we can be write down the epsilon naught E into the cross sectional area, that is the A naught, plus epsilon I E into AI equal to 300 into 10 cube. So we know that one the strain value, that is the strain for the outer bar, that is the delta by 1000. Here we have to substitute. So epsilon naught equal to should be delta by 1000 into the E. So A naught cross section area outer bar plus strain in the inner bar, that is also we know that one the delta minus 1 divided by 999. So into Young's modulus into cross sectional area of the inner bar equal to 300 into 10 cube. So in the given data already given the cross sectional area of the all the bars, that is 2 outer bars are there. So cross section area of the each bar having the 2500. So here cross section area of the outer bar is 2 into 2500, that is the 5000, and Young's modulus of the magnesium material is given 4.5 into 10 cube and delta by 1000. So here also same thing, E value is 4.5 into 10 to the power of 4. Cross section area of the inner bar, that is having the only 1 bar, so that is the 2500 equal to 300 into 10 cube. So substitute the all the E value and A cross section areas value in this equation. So we will get that one delta by 1000 into 4.5 into 10 to the power of 4 into 5000 plus delta minus 1 divided by 999 into 4.5 into 10 to the power of 4 into 2500 equal to 300 into 10 cube. So then we have to solve this equation. So we will get the delta value equal to 1.222. So 1.222 mm. So which is nothing but deformation of the outer bar. So the problem is given that find the downward displacement of the rigid plate. See here, so the displacement of the rigid plate should be equal to the deformation of the outer bar, that is the delta. So which is equal to the 1.222 mm. So this is the solution. So thank you.